Hello. So today let us see alkenes in a great detail. So today our only aim is to look at a specific reaction of alkenes in preparatory methods. So that will be dehydrohalogenation and we will do some elimination basics. So what are alkenes? Alkenes are unsaturated compounds. They have double bond in their open chain. They are open chain compounds with double bonds. So they have unsaturation. And then what else? So they are also called as olefins, right? And then their degree of unsaturation is one. They have one double bond. So their general formula is given by CnH2n. Okay, and then they generally undergo addition reactions. They undergo addition reactions. We'll discuss more about addition reactions in properties of alkenes. Alkenes. So let us see preparation of alkenes. So the first major preparation we can see here is dehydrohalogenation. So I have written others also here, that is hydrogenation using Kolb's electrolysis and using elimination reactions. So today our goal is to only look at dehydrohalogenation, which is a pretty important topic in the whole alkenes chapter. So let us start. So today our topic is dehydrohalogenation. What does the name suggest? Dehydrohalogenation. So you have something to do with hydrogen and halogen, right? So HX, hydrogen and halogen, is being removed. So elimination of HX is called dehydrohalogenation. So this reaction is performed in basic medium. Okay, so you take alkyl halide, and in basic medium when you heat it. So why are you heating it? Elimination reactions occur under heat. Like when there is heat, probability of elimination would be more. Okay, so in basic medium, you take an alkyl halide and then you heat it. Then alkene is formed with some HX. Okay, HX is eliminated. That is why this is an elimination reaction. So dehydrohalogenation can be explained through all the three elimination reactions of beta elimination, E1, E2, E3. So, sorry, E1, E2 and E1, CP. So we'll discuss about them shortly. So we can clearly see you take alkyl halide base and then you heat it, alkene is formed. That's the basic skeletal structure. Now what are the reagents? So the reagents generally mostly used are alkaline NaOH or KOH or triethyl nitride, or we use ethanol as solvent, and the ions, K plus or Na plus, which act as electrolyte, and then NaNH2 or sodamide. So these are the important reagents which are generally used for dehydrohalogenation. What you need is a basic medium to perform the reaction. So in dehydrohalogenation, we have seen that alkene is formed. Now, there are cases where two different alkenes can be formed. For example, we can see here in this example. So in this example, we have an alkene here, and then we are doing the same. We took the reagent here, okay, and then this will be broken, and then a double bond can be formed here, or a double bond can be formed here. So when the reaction is done, two products are formed. One will be a double bond here and a double bond here. One will be major and one will be minor. How do you decide which is major and which is minor? So this is decided by stability of the product. So stability of product, we can go to our GOC and check. So here, hyperconjugation we have to check. You can see here we have four alpha hydrogens here, right? We have four alpha hydrogens, but here, so this is the functional group, right? So we have six alpha hydrogens, but here we have this will be alpha, two alpha hydrogens. So when there are more alpha hydrogens, generally what would happen? There will be more hyperconjugating structures. When there are more hyperconjugating structure, the product or the structure we are discussing is more stable. So here we can clearly see which is more substituted will be the major product. So that this is more substituted, more hyperconjugating structures. So that will be the major product. So that one was only transformed into rule. So that rule is called Zaitsev rule or Zeister elimination, which is a very important name. Okay, what does it simply say? Mode substituted is the major product. So when alkyl halide has more than one type of beta hydrogen, means now the alkyl halide is turning into alkene. So what are the beta hydrogen? So this is the functional group, right? So this will be alpha carbon. This is called alpha carbon, and these two positions are called beta carbons. So we have a primary beta carbon and a secondary beta carbon. So and similarly we'll have beta hydrogens. So when there are more than one type of beta hydrogen, uh, more than one alkene is formed, which we have seen here. So, which will be the major product? More substituted is a major product. What is more substituted? Which has more hyperconjugating structure, right? So that is called Zaitsev elimination. So order of reactivity of alkyl halides is pretty simple. So tertiary alkyl halides undergo better dehydrohalogenation than secondary and then primary. Okay. So this is something which we have to remember, order of reactivity. And then similarly, contrary to the Zaitsev elimination, we have something called Hoffman elimination. So what is Hoffman elimination? It is just the opposite. Less substituted would become the major product. Why? We have clearly seen we got a simple logic that more hyperconjugating structures will be more stable. Then why the less substituted will be the major? So this case arrives when there is a bulky base. So you can see here in the second example. This is the first example. This is the second example. So let's focus on the second example first. So in second example, you can see that we have an alkyl halide like this, okay, and then the base we are using is a tertiary alcohol. Tertiary alcohol is big. It has three methyl carbon, like three R chains around the carbon. So tertiary alcohol, it has to attack. Now, what we have seen in the basic dehydrohalogenation reaction, so hydrogen will be like the bromine will be removed, and the hydrogen gives a double bonds, and it will be removed. Bromine will go, it will get a positive charge, and then hydrogen will give its electron, and hydrogen will go forming HBr. That is dehydrohalogenation reaction. We'll discuss the mechanism more deeply later. So, but here, what would happen? The bromine, so let's consider a hydrogen here. Hydrogen here. We have two cases. So, according to the Zaitsev elimination, what does Zaitsev elimination say? More substituted will be more major product. So, what are the two cases? So this hydrogen can give electrons and then HBr is formed like this. Or this hydrogen can give electrons and then another product is formed like this. See, now what is major and what is minor? So when we see the factual data, this will be the major product and this will be the minor product. But we have just seen that we have to check the alpha hydrogens and the more number of hyperconjugating structures. Clearly, this structure has more hyperconjugating structures. But why this? Here it is depending on base. So it is a hindered base, means a tertiary alcohol is pretty big. Now, this base has to go and react. Okay? The base goes and reacts. That is why the bromine is coming out. That is why the hydrogen is coming out. Okay? The hydrogen has to come out. Means the base should go and interact with the molecule. So if this hydrogen has to come out, the base has to go here. So here we have pretty large groups and the base itself is pretty large. So we get a term here which we have studied in the GOC. It is called SIP, steric inhibition of protonation, or we'll just say steric hindrance. Okay. So because of steric hindrance, there will be repulsions. So this base would rather go and attack this hydrogen than go and face the repulsions on the other hydrogen. So that is why this will be the major product and this will be the minor product. So in case of bulky base, we made a new rule. Okay. In case of bulky base, lead substituted will be the major product because of steric hindrance. So that is called Hoffman elimination, or this is the Hoffman rule. When alkyl halide has more than one type of beta hydrogen, more than one alkene is formed, like similarly. So here more than one alkene is formed. And then, but due to the bulkier base and steric hindrance, lead substituted will become the major product. That is called Hoffman elimination. We have clearly seen because of bulky base, the groups are very big, so they react. Like repulsions are seen. So because of repulsions, what would happen? The base would rather choose a better option than the repulsions, right? So that's pretty simple. Now we have a small example here. So we have bromine, we have a tertiary alcohol. Okay, so this ethanol will go in ethanol, tertiary alcohol, tertiary alcohol, right? So what would happen? A bromine can give its can. So what are the two possible products like this? One will be this, and the other one will be this. Okay, out of these two, which will be major product? So here there is no bulkier base. It is ethanol, pretty simple base. So more substituted will be major. This is more substituted, so this will be major, and this will be minor. Okay, so let's discuss the mechanism in the dehydrohalogenation reactions. So before discussing that, let's see elimination reactions. Okay, let's discuss elimination reactions in pretty detail. Now, elimination reactions are basically of three types: 1-1 elimination, 1-2 elimination, and 1-3 elimination. Or it is called alpha elimination, beta elimination, or gamma elimination. So what is alpha elimination? On the same carbon, on the same carbon, you have the hydrogen and the alkyl, the halogen group. Halogen group and hydrogen are on the same carbon. So this carbon is called 1. So when dehydrohalogenation takes place, HX is removed. So 1-1 on the same one carbon, it is elimination happening. So HX is eliminating on the same carbon 1-1. So that's why it's called alpha elimination. Now what is beta elimination? So here we have two carbons, and we have one hydrogen here, one halogen here. So if hydrogen is going like this, halogen is going like this. So this is called 1, this is called 2, or the reverse. So 1-2 elimination. On the first carbon and the second carbon, elimination is going on. Okay. So this is called 1-2 elimination or beta elimination. What is 1-3 elimination? So 1-3 elimination is also called gamma elimination. So this generally happens to form cyclic ethers. So let's say we have it like this. We have a halogen here, and then we have a hydrogen here. So here 1-3, 1-2-3. So 1-3 elimination is going to take place. Okay. Here it is oxygen. That's why the third carbon is going on. The third atom is doing elimination. If it were not oxygen, the second carbon would lose the hydrogen. So 1-3 elimination would take place, and then a cyclic ether is formed. Such kind of cyclic ethers are called oxyrenes, or they're cyclic ethers, right? So this is called gamma elimination. So keeping alpha and gamma aside, let's discuss about beta elimination. Because beta elimination is of again three types: E1, E2, and E1 CB. Okay. So E1 is called unimolecular elimination. E2 is called bimolecular elimination. E1 CB is unimolecular conjugate base elimination. Okay. Let's discuss them pretty simply. So let's discuss about E2 elimination first, and then let's come to E1. So E2 is called bimolecular elimination. That's why you represent it with a 2. Okay. Order of reaction is 2. What is order? It is a property of reaction we have seen. Order is experimental based. So when we have done experiments, so we have seen that the rate of the reaction, or how fast the reaction proceeds, the rate is directly proportional to the concentration of the alkyl halide you are taking, and also the concentration of the reagent, the base you are taking. So the rate is depending on two factors. That's why the order of reaction is 2. Okay. So we have anti-elimination or thin elimination or anti-elimination. We will discuss in stereochemistry of E2 later. So we can clearly see here the order of reaction is 2. So there are many reaction. Dehydrohalogenation is an example of E2 elimination. Okay. So what is happening in E2 elimination? The hydrogen will go like this. The halogen will go like this, and the double bond is formed. Okay. So leaving group leave from opposite sides. That is why we call it anti-elimination. What is anti-compound? From isomerism, do you remember? Opposite sides are called anti, and then similar sides are called syn. Okay. So if anti-elimination takes place, the groups leave from the opposite side. Like H goes from the top and X goes from the top bottom. Okay. So that is called anti-elimination. And more important thing, E2 reactions, so they are one step reactions, okay? Right? They are one step reactions, and there is no intermediate formed, and everything is endothermic. Means delta H is positive. Energy is absorbed. Okay? So that is it with E2 reactions. So what is E1 reaction? E1 reaction is unimolecular elimination, E1 reaction. Okay? So here why did we name E2? Because order of reaction is 2. So E1 will be order of reaction is 1. Means the rate is dependent only on the concentration of alkyl halide, but not the reagent you are using, not the base. Okay, so that is why the order of reaction is 1. It is called even reaction. So again, it is an endothermic. Sorry. Wait a minute. Okay, so it is an endothermic reaction, and an intermediate is formed. Carbocation is formed. So weak base polar solvents are used. That's when even reactions take place. Okay, so it occurs in two steps: the carbocation formation and the elimination of the leaving group. Okay, so let's see. And other properties of even reactions are, so carbocation rearrangement. C plus represents carbocation. Okay, so carbocation rearrangement takes place if possible, and then order of reaction is when delta H is positive. Okay, now for example, we have an example of even reaction here. So let's see the mechanism how even goes. So E2 is pretty simple. It is a one-step reaction. Even. Now even is, you are going to take we are going to see the mechanism of this compound. This alkyl halide, a tertiary alkyl halide, is going to undergo and some reaction, and it is going to form alkene. Let's see how. So first step will be formation of carbocation. So how will it happen? So this is the um, alkyl halide we are having, a tertiary alkyl halide, and in presence of H2O, what is happening is the chlorine is getting released as Cl minus, and carbocation is formed as C plus. So this step is the rate determining step. Rate determining step is because of this step, the rate of the whole reaction is determined. So if the rate of the reaction is determined by this step, it should be slow. Okay, so RDS is always a slow step. Okay, so first, because of H2O, means H plus is going to attack. So when H plus is going to come towards this carbon, what would happen? Cl would gain negative charge, and it would come out, and then carbocation is formed. Okay, so the step 2 will be alkene formation and elimination. So we have clearly seen here the hydrogen which is on this carbon. Okay, so this is the carbocation. It is electron deficient species. So the water which we are using as solvent, okay, the water would react with, like, it would do some magic. Sorry. So it would react with this hydrogen with the adjacent carbon, and what would happen? H3O plus is released, and then this hydrogen would give electrons, right? It will come out as H plus. It is giving electrons. So this electron carbon is negative charge, and then a double bond is formed. That's what you can see here. Alkene is formed with H3O plus is also formed here. Okay. So this is how an E2 reaction would take place. Okay. E2 reaction is, this is the mechanism. So in E2 reaction, sorry, even reaction. So in even reactions, we have rearrangement of carbocation possible. So how is that possible? Rearrangement of carbocation. Rearrangement of carbocation can occur in three styles. So there can be a hydride shift, there can be a methyl shift, or there can be a ring expansion. Okay. So let's see an example of hydride shift. So this is a compound here, and you are going to do an even reaction. So what would happen? This OH should release, and then the H plus would come and attack them. Okay. So the first step is formation of carbocation. Okay. The carbocation formed will be like this. Okay. The carbocation is here. This is the primary carbocation, 1 degree carbocation. Now, there is a possibility that this positive charge can, like, it can shift here. So what happens if the possibility that this plus charge would shift here, then a tertiary, like a 3-degree carbocation is formed, and we have studied in inductive effect that 3-degree carbocation is more stable than 1-degree carbocation. Now, so we have to make sure that this plus charge would shift there. So how will this take place? Now you have a hydrogen here, right? You have a hydrogen here. Now what would happen? This hydrogen, it would give electron, or sorry, so hydrate, right? So it would take electron. It would take electron and forms H minus. It would take electron, then a positive charge is formed here. And then this H minus, it goes and attacks this positive charge. Then what would happen? The hydrogen will be here, and then the positive charge is here. See, this carbocation is more stable. Okay, from here, you can say that when you do dehydrohalogenation, what would happen? After the carbocation formation, double bond is seen like this. So, if you didn't do hydride shift, what would happen? If this went, this will be the positive charge. Okay, if this were to be the positive charge, how will be the double bond? Right. So, because of hydride shift, this product is being formed. Okay. So this is called hydride shift. So H minus is going to go and attack the positive charge, and rearrangement of the plus charge will take place so that the intermediate is more stable. If intermediate is more stable, the product will be more stable. Pretty simple. Now, methyl shift. Now we have a alkyl halide setup here, not alkyl halide, some this thing. Okay. So what would happen? Now we have a phenyl group here. What is phenyl group? Just the benzene group. We have a phenyl here. Now H plus is going to attack. Then OH minus would come out. OH minus would come out, and the first uh, this thing you are going to get intermediate is this, and then you have a hydrogen. Now you see here, this is a secondary carbocation, 2-degree carbocation, but there is a chance that here it will become a 3-degree carbocation, and also because of this phenol group, sorry, because of this phenyl group, extended conjugation take place. So when there is extended conjugation, like we know that benzyl carbocations are pretty stable, right? So that will be pretty stable. So in order to form that pretty stable intermediate, what would happen? You don't have hydrogen to shift here. If there was hydrogen, you can shift hydrogen and bring positive charge here. You don't have hydrogen on this carbon to shift. Then you are going to shift a methyl group. See, now what would happen? So this methyl is going to come out. Okay, this methyl is going to come out, and then what would happen? A positive charge is formed here, right? A positive charge is formed here, and then CH3 minus, and it will again go and attack the this center, electron deficient center. So what would be forming? Like this. So this methyl group has shifted here, and then carbon, and we have P. See, now because of extended resonance, this intermediate is pretty stable. Extended conjugation, this intermediate is pretty stable. So that is why after the dehydrohalogenation takes place, the double bond is formed here. Okay. Otherwise, the double bond would also form here. This will be a minor product. This will be a major product. Now, this is methyl shift. Now, ring expansion. When there is possibility of ring expansion takes place. How will that happen? So you can clearly see here we have a cyclopentane with a OH group like this. So H plus would attack, OH minus would come out, and a positive charge is seen here like this. Okay. This will be the positive charge with you. Now, here we have a hydrogen. Now, what would happen? Ring expansion. So, 6-membered ring can be formed, right? 6-membered ring can be formed. How will that form is, so this bond which you can see here, I'll use a different color. This bond you can see here, this bond would break apart. If this bond will break, this will get a positive charge, this will get a positive charge. Okay, so what would happen? Like this. Yeah, this will be a positive charge, this will be a positive charge, this will be a positive charge. Right. Now, what would happen next is this positive charge and this positive charge will form a bond like this. So thus a six-membered ring is formed. Okay, you can see here, right? A six-membered ring is formed. So 1, 2, 3, 4, 5, 6. So the intermediate thus formed will be like this. It's looking ugly for now, and later we'll rearrange this. Okay, so this will be the intermediate form. After dehydrohalogenation, a double bond is formed here or here. Both mean the same, and thus, sorry, and thus the product form will be like this. So without ring expansion, you can't explain this product. But because of ring expansion, you can see this is a product formed because of this dehydrohalogenation. So this is with even reaction. So we have even CB. Even CB stands for elimination unimolecular. Just give me a minute. Right. So even CB stands for elimination unimolecular. Unimolecular conjugate base. Okay. So here rate determining step is unimolecular, but the overall reaction is going to be bimolecular. So what is the first step in even CB? Formation of C minus is seen, and then later formation of alkene is seen. That would be step 2. This takes place when there is a poor leaving group or there is conjugate base of withdrawing. Like, now let me tell an example. Okay. Right. Chlorine, chlorine, uh, fluorine, fluorine, carbon, and then hydrogen. Okay. Now, OH minus is going to attack. Okay. So OH minus is going to attack. H plus is going to leave. OH minus is coming to attack. So H plus is going to leave. Right. So what is the intermediate form? A carbanion. See, now we have a carbanion here. When there is carbanion, what is happening here? So these are minus I groups. So minus I groups are electron withdrawing groups. They are going to take electrons and nullify the negative charge on the C minus. So when the negative charge is nullified, the intermediate will be more stable. So we call this conjugate base, right? Because H plus is coming out. This is called conjugate base. Now the conjugate base is pretty stable. Now this is going to happen really fast, but the rate determining step will be leaving of fluorine. Leaving of a withdrawing group is going to be a rate determining step because fluorine won't leave easily. So that is why the rate determining step would be leaving of withdrawing group because conjugate base is pretty stable. So chlorine, the carbanion is formed very fast. So this is fast, but the rate determining step is leaving of withdrawing group. C and then a positive charge is there, and thus a double bond is seen. So such kind of elimination reactions are called even CB, where the conjugate base is pretty stable, and because of poor leaving group and withdrawing groups present to the beta carbon. This is the beta carbon, right? Out of fluorine and chlorine, fluorine leaves faster than chlorine, right? Okay, so C minus and then a double bond is formed. Pretty simple. So this is even CB or even conjugate base, unimolecular conjugate base. Now stereochemistry of E2 reactions. So we can clearly see E2 reaction is regioselective, right? And then there are two types of elimination here. So syn elimination and anti-elimination. If hydrogen and bromine are going to leave from the same side in this form, okay. So this is called syn elimination. And if hydrogen and bromine are going to leave from the opposite side, it's called anti-elimination. Okay, these are the conformal states. And E2 elimination is more regioselective. And we know E2 reactions are of two types of elimination takes place. That is Zaitsev elimination and then Hoffman elimination. Zaitsev elimination is more substituted is major. Here the base is normal. Okay, and Hoffman elimination takes place when there is a bulkier base. So so when there is bulkier base, stereochemistry we can discuss there, and then bulkier base, then the less substituted will be the major product. So that's it with dehydrohalogenation. So in next video, let's see Cope's elimination and some other elimination reactions, and let's complete the preparation of alkenes. Right? Thank you.